Welcome back to Differential Calculus. In this video, I want to talk about implicit differentiation. If you just read a definition of implicit differentiation, it seems kind of dry and boring. So rather than stand here and talk about it, I do want to jump into some pictures and analyzing what's going on. Before I do that, though, I do need to get my head out of the way and go through one definition here. Any curve in the xy plane can be read as implicitly defining y as a function of x on some part of that curve. To see what I mean, let's jump into Desmos, where you can see I have a curve, x squared over 25 plus y squared over 9 equals 1. There's also another curve behind my head, which I'll get to in just a moment. But the curve here defines an ellipse, and very clearly an ellipse is not a function. Any vertical line I come across that passes through the ellipse at all is going to pass through in two places, except for at the very extreme over here and the very extreme over there, but anywhere else that will be a problem. Right? So this is not a function. The idea, and the reason I have this other curve written out, is what if instead of thinking about the entire ellipse, I just think about a piece of it? And I've highlighted here the piece in the third quadrant. Within the third quadrant, it is suddenly the case that y is a function of x. And as soon as we have that, we are able to work with it. So that's what we're talking about when we say we are defining a function implicitly. Right, back to my notes. Now that we have an implicit function, let's write that same formula, x squared over 25 plus y squared over 9 is equal to 1. And I'm going to leave it as an exercise to you if you're interested in doing so. But let's say that I wanted to find the equation of the line tangent to this curve at the point -4, -9/5. Well, we know that this is implicitly defining y as a function of x on the third quadrant where this point exists. And we know that if we have y as a function of x, that we can find the derivative and use the derivative to write the equation of a tangent line. And that's what we want to do here. I will address the elephant in the room. In this particular function, it is possible that we rearrange the equation to solve for y. And when we do that, then we run out of issues and we could proceed without any further problems. I don't want to do that because I want to show you a method that is generalizable. I want to show you a method that will work no matter what is going on with x and y. And in fact, in the next example I go through, it is going to be literally impossible to solve for y as a function of x explicitly. So even though there are other options for this particular equation, let's go with it anyway. All right. So the method that we are looking at is called implicit differentiation. And the way this method works is I am going to take the derivative of the entire left-hand side of the equation. And I claim that because the left-hand side and the right-hand side of the equation itself are the same thing, if I take the derivative of the left-hand side or the right-hand side, it should still be the same thing. Taking the derivative of the right-hand side is really straightforward. The derivative of a constant is always 0. the left-hand side gets messy. Right? There's two pieces, so I can separate that out using linearity. So we'll have 1 over 25 times the derivative of x squared, which is 2x. Then we will have 1/9 times the derivative of y squared. Well, the derivative of something squared is 2 times that thing, so it'll be 2 times y, but y is a function of x. So we have to use the chain rule here and further differentiate. The derivative of y is y prime. Now, from here, we can solve for y prime. I'm not going to write out all of the algebra, but just do some algebra to rearrange and solve for y prime. And you should get that y prime is negative 9x over 25 times y of x. Now, that in and of itself was quite messy. What makes it even messier is that when we're doing implicit differentiation, we never write out the of x. We always omit it because it wasn't there in the original problem. So we say we're going to take the derivative with respect to x of x squared over 25 plus y squared over 9, and we say that that's going to be equal to the derivative with respect to x of 1, same as we had before. Using the chain rule, even though it's not there, right? Derivative of x squared over 25 is 2x over 25. The derivative of y squared over 9 is 2y over 9, but I just took the derivative of y, and y is a function of x, so I have to multiply it by y prime using the chain rule. It's the exact same thing. The only change between how I wrote out in white and in yellow is whether or not I put the of x on things. But as soon as you remove that, it suddenly feels like it's this magic, right? Where did the y prime come from? The y prime came from the chain rule because we're taking the derivative with respect to x. When we take the derivative of x with respect to x, there's nothing to worry about. When we take the derivative of y with respect to x, we have to implicitly assume that y is a function of x and write in its derivative. We'll see in a future video that this can get even worse. We can have 3 or 4 or 5 variables, and it could be that none of those variables are the thing we're taking the derivative with respect to. It still works. It still gives you the same result. It helps if I push the right button. There we go. Right. But however we do it, we do end up with y prime is negative 9x over 25y. I'm just going to rewrite that over here for the sake of convenience. Y prime is negative 9x over 25y. And remember what we were trying to do. We were trying to find the equation of the tangent line at the point -4, -9/5. And from here, everything works the same way. The slope of the tangent line is y prime at -4, -9/5, which means it's -9 times -4 divided by 25 times -9/5. -9, -4 is positive 36. 25 times -9/5 is -45. Those are both divisible by 9, actually. And so we're going to end up with I lost a negative. we're going to end up with -4/5 as the slope. From here, y minus the y coordinate, -9/5 minus a minus is plus, is equal to the slope, -4/5, times the quantity x minus the x coordinate, -4. And rearranging that just a little bit, y equals -4/5 x. That is not correct. It is not +1. Y equals -4/5 x. We'll have -16 minus another 9 is -25/5, which is just -5. Now, if I jump back to Desmos and I graph, y equals -4/5 x minus -5, we can see that it is tangent. It hits the curve at exactly one point, and that exact one point is -4, -1.8. So we do, in fact, have our tangent to our curve. All right. There's the idea of implicit differentiation. If I jump back to the notebook here, let's look at one more problem for you to take a look at this time. I want to look at y times the cosine of x plus x times the sine of y is equal to 1. I would like you to implicitly differentiate this curve and find an expression for y prime. It is going to have both x and y in it, and that's perfectly okay. All right, so no further than that. I'm not giving you a point. I'm not asking you to write the equation of a tangent line. I'm just asking you to work through the implicit differentiation, being careful to use the chain rule. Take a couple of minutes to see what you can do with that one, and I'll see you in the next video.